so we're continuing in 15.1, which was an introduction to vector fields. We stopped with the gradient last time. Let's just remind ourselves of that. So find the gradient of f of x, y, z equal to, let's say x squared e to the x, y, z. So I think last time we just did an example in a vector, two-dimensional vector. So same thing with a function of three variables. You can do this three-dimensional gradient, so f sub x, f sub y, f sub z. You're just computing these partial derivatives. So take a second. Try to compute those. Okay. So for f sub x, just be careful. You need to do a product rule, right? So what do you get?
2x times e to the power of x y z plus x squared times yz times e to the power of x y z.
Good. Everybody getting that? Right? You take 2x, the derivative of that x squared, and then times that e plus x squared, and then the derivative of the e will kick out the yz. And then similarly for the other ones, right, the x squared just sits there, and then the derivative with respect to y will be e to the xyz, and it'll kick out a xz, right? So you should end up with x cubed z e to the xyz. And then finally,
That's 2y to the power
okay? All right. So let's, I'll call this a definition. I don't think your book states it as a formal definition yet. They might do that later on. So f is conservative if, so this is a vector field, so vector field f is conservative if f equals the gradient of little f for some f, and then in this case, little f is the potential function for capital F. Maybe I should say a potential function. And so this, I mean, the terminology just comes from a field where force is conserved or where energy is conserved. Is it, you know, turns out to be the gradient of some little f, and so that's where this terminology comes from. We don't need that right now. I just want us to play around with this idea. So let's. So we're going to have nice tests for whether a vector field is conservative or not that don't require you to do anything too clever, but right now I want us to just go in sort of blindly and we'll just fumble around and see if we can figure it out. Okay? So determine if the following are conservative so, I mean, I'll just. Actually, let's just do this on y, x. No, let's do this. Yeah, that's, we'll start with a real, hopefully a very basic one. All right, so capital F is the function or the vector field y comma x. And so we want to decide if this is conservative. And so let's say the work you'll do for here. Being conservative means you are equal to the gradient of some little f, right? So it means whatever this f is should have this form, right? So if this guy here is conservative, so if conservative, then there is little f such that what? F sub x equals y and f sub y equals x, right? So if you've taken differential equations already, you've done something very similar to this. There. But let's just work through this, okay? So we just start with one of these and we try to build our f up from there, okay? So I'm not always going to do this, but if you just start with the f sub x, that's usually fine. I mean, it's always fine. Sometimes there's situations where it makes sense to start with the other. But let's just do this. So we're assuming such a little f exists, and then we're going to try to build it. And then if we have problems, we'll come back and realize we can't do it, or else we'll try to get over those problems. So if a function has the form where, or if the function has the property that its partial derivative with respect to x is y, then f has to look like what? xy plus, so essentially you're integrating, right, with respect to x. Right? You take the integral of that with respect to x, you get xy. Well, plus c, but the c is really bigger than that. The c could have y's in it, right? Because anything that was just y's, when you take the derivative with respect to x, will disappear. So we're left over with a constant with respect to x, but it could have y's. And so when we say constant, we just put a constant g of y. Does that make sense? So this one, it'll be fine, but we'll see that that comes up later on. Because when you differentiate this, right, if you had any function y, that'll disappear when you go back up that way. Okay, so then we take this function, and we take its derivative with respect to y. What is that? No, well, it's x, right? With respect to y, and then plus g prime of y, right? The derivative of whatever y was. Does that make sense? And then what do we want that to equal?
12.
The f sub x, or f sub y that we had over there, right? Which was x, right? And so we want this. So x should equal x plus g prime of y. So does that make sense? And so the g prime of y we can just assume is 0. And so g of y could be a constant, right? But we don't care about constants. We just want to find one potential function. And so what this shows you is, so f of xy equal to xy is a potential function. For our capital F, right? And so this isn't part of the problem. Let's just see that, right? Again, gradient of this little f, as we just saw, right? Derivative with respect to x is your y, with respect to y is your x, right? So that's a nice potential function. Okay, so now let's try some that get just a hair uglier. Actually, let's do one other one that's really easy. Actually, I'm all over the place. Let's do one tricky one and then we'll come back and do it. And when I say tricky, I don't know how tricky. Okay. So let's do this. E to the x cosine y, comma, negative e to the x sine of y plus y. All right, so try the same thing we just did. All right. Let this, and you don't have to show every step, you can just say, start like this. F sub x is e to the x cosine of y. Find f from there. After you find your potential f, take the derivative with respect to y. Again, keeping in mind that's what we think f sub f sub x, f sub y should be. Okay, so let's finish this off. Okay, come back and do this. So we assume f sub x is this guy, right? And then what's f if we integrate that with respect to x?
Yes.
Just
Times cosine y plus g of y. Right.
so just the exact same thing, right? And now we differentiate with respect to y, and what do we get? Negative
Sine y
plus g prime of y, right? The derivative of that g. Does that make sense?
So in the first step, we get the integral with respect to x.
Yes, so this is, you just integrate with respect to x, and then once you have that, you differentiate with respect to y. Again, keeping in mind could be some function of y. And now this has to equal that left-hand side if the function's conservative. And so we need negative e to the x sine of x plus y to be what we had. And again, this might not be possible, right? And if it's impossible to come up with such a function, then we know it's not conservative. So what does that mean here then? So g prime of y must have been negative y. So what's g of y?
y squared over half.
Negative y squared over 2 plus a constant, but we always just leave off the constants here. And so then, so f is conservative with potential function f, and that f is e to the x cosine of y plus the g, right? So that's minus y squared. Does that make sense? Okay. Again, we'll keep coming back to this, and we'll develop sort of better tests to know when something's conservative and when it's not. But let's do one where it's not conservative, and so we'll just have to see that this is impossible to do this time. Okay? So this time, our f is, let's just use other notation. So yi plus xyj, right? So that's just using the unit normal vector notation. Basis unit vector notation. Okay, so again, this should be, if it's potential, that'll be your little f sub x, that'll be your little f sub y, right? So, let me have you try that one for a second and then do this one. So, try this one. Again, if you try the method we used, you should run into a insurmountable problem and then you'll conclude that it's not conservative. That's not an ideal way to do problems, right? Because it's not always clear that the problem is insurmountable. And so we'll have tests for this in later sections. But for right now, we just want to kind of fumble through that. And so if you either finish this one or you get stuck on this one, move on to the next one. There we just have 3 variables. And so the idea is still the same. It's conservative if that's f sub x, that's f sub y, that's f sub z. And, well, I'll have you think about it for a minute. Do both of these together. So let's try to work this one out and just see, again, in a few sections. This is definitely not the approach that we would take to do this one. So f sub x is y. What's f sub, or f then? xy plus g of y. And then you take f sub y and you should get x plus g prime of y. Okay? And if it was conservative, then that should be equal to what? xy should equal x plus g prime of y, right? And so so g prime of y would be xy minus x. But g prime of y is just a function of y, right? There shouldn't be any x's in it. And so since there's x's in here, everything just falls apart. Does that make sense? So I'm just going to say this, not. And we'll introduce nice methods to prove this. In fact, this one's pretty easy to show. Remember with partial derivatives, the mixed partial derivatives were equal to each other. The derivative with respect to x then y was always the same as y then x. There's some caveats to that, but essentially that's true for any function you work with. And so if you assume this guy was f sub x and this guy was f sub y, so for this example, let's call this p and q, okay? And so if it's conservative, p sub y is f sub xy, right? Because that was f sub x, but what would that be? What's the derivative of that with respect to y?
Watch that one.
1 q sub, so if conservative, q sub x would be f sub yx then, right? But what's q sub x?
6 of what?
Yeah, it should be, it'd be y, right?
Yeah.
And they're not equal, so. That makes sense? So that'll essentially be our test for whether a function, the vector field is conservative, a two-dimensional vector field, and then the curl, which we'll introduce later, will give us a nice test for three-dimensional vector fields. Okay, so this one will work the same way. F sub x is y. What's f then?
x1
xy plus what?
plus
Of y and.
G of y and z, right? Because we have three variables now. And so when you differentiate with respect to x, you'd lose both at y's and z's, right? Does that make sense? You'd lose.
Can I divide it into g of y and h of z?
No, because they're not necessarily added together. They could be, right? You could have, this guy could be y z squared or something, right?
Okay.
And it would still be 0 when you take its derivative, and you can't write that as g of y plus h of z. Does that make sense?
Okay.
So it needs to be a function of both. In this case, you would have been fine. It would have worked out, but you should think of it as a function of both. So now I do f sub y. What do I get?
X plus g prime.
X plus, and don't g sub y, right? G is now a function of two variables, so you want to take its partial derivative. And you get that.
Two.
And what do we want that to equal?
0.
Right, well, we want the whole thing to equal x, right?
Oh, yeah.
So g sub, so that means g sub y of yz should be 0, which means g of yz is really just, I'm going to keep using my g. It's really just a function of z, right? There's no y in it because the derivative with respect to y is nothing. And so that gives us that our f is just xy like we thought it should be, and then some function of z, right? And then you take the derivative with respect to z, and you get
G.
0 plus g prime, and we want it to be z cubed. So g is 4, and so your f of xy is, is that okay? Where am I at?
There is a z inside f x y z.
Oh, you're right, you're right. I usually will just write little f without, as I have been, without putting in the variables, but yeah. Does that make sense? And so, well, I guess we got, so it's conservative with potential function. This guy. Okay, I think there's maybe one or two examples in the homework. There's not a whole lot with this right now. We'll come back to this later on. Okay. So, all right. So divergence. The book spends a bit of time talking about divergence. We're going to have a really important theorem later on called the divergence theorem. For the most part, it's going to be just this tool for us to use. And so in this section, the majority of the problems are just practicing computing divergence. The divergence is sort of a measure of the outward flow of a vector field. And so if you have, if you have all the vectors pointing away from someplace, you're going to have positive divergence. If they're all coming back in a direction, you'll have a negative divergence. And so essentially, positive divergence means stuff spreading away from your point. Negative means it's accumulating at your point. And then zero divergence, if you had a vector field that was just moving along in some straight line, roughly. Stuff's just flowing through, you're not gaining or losing anything, you're kind of keeping a fixed amount. Does that make sense? So that's kind of just a broad idea of what divergence is measuring. I don't think I want to do any more than that for now. Maybe we'll come back to details in a bit, but let's just let's show how to compute it. So if F is this vector field Pi plus Qj plus Rk, okay? And you could drop off the R, right? If you want a two-dimensional one, just follow the same formula. Then the divergence, which we denote by div of F, is simply the partial derivative of P with respect to X plus the derivative of Q with respect to Y plus R with respect to Z. And so that's not too bad to memorize, but we're going to do something here, which is we're going to start viewing this nabla as an operator, okay? And so it's the operator partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z. Okay? And in this way, you can think of this as, so this is sort of abusive notation, but I think it's okay. I think it's helpful, it makes sense if you think about it, as the dot product of these things, right? So you take the dot product of this vector, or of this operator, it's really an operator, and you dot it with f, right? And so it should be the partial of x times the p, right? And so instead of times, you do of the p, that's your piece of x, right? Plus, the dot product does then the partial of y of your next function and so on. Does that make sense? So this is sort of the convenient way to remember how to compute the divergence. Okay? And so let me have you compute a few, and then I'll bring up some graphs on the computer. So example, compute. Compute the divergence of f. And so these will be should be very short. And actually we'll even do some really basic ones. So all those were just simple ones in 2 dimensions. This is really just a way to make you practice some partial derivatives. So, compute the divergence of each of those. It should be pretty quick. I'm going to pull up some graphs. Okay. So let's just start working through these. So I'm gonna, rather than write divergence, I'm just gonna keep writing with the gradient operator here with the nabla, or the del operator. So del dot f. So what should we get in this case? 0. Everyone okay with that, right? Partial with respect to x, with respect to y, they're both 0. How about this one?
Y plus
1 plus 1, so 2, right? So partial derivatives. Cases, how about this one? Another 0. How about this one? Minus 1, minus 1, right? So negative 2. Okay. 3 dimensions, what do we get here? 3 x squared plus 3y squared plus 3z squared. Should all be hopefully pretty easy. And then the gradient with respect to f. Y squared minus 4. Does that look okay? All right. So let's just take 1 second and look at the vector fields of these things, as long as we have them here. Let's see if I can manage to get this screen to come back up. I'm not going to fall down all the way. All right, so this isn't, I wonder if that camera is physically moved or if you're able to move the screen. But it's all over the place, whether you can see it. Shake the screen and show up. All right, still off screen a little bit. Just scoot this over. Okay, again, I'm not worried about any great details here, but just let's look at these simple examples we did. So the first one, you had 0, and so again, the divergence is really a property of individual points, but let's just think of it as a big thing. So that first one, we had a divergence of 0, right? And so that's why I said net outward flow would be 0. And so let's just think about this whole box as our region. Notice that you got a bunch of stuff leaving here, right? If you think of these arrows representing like fluid flowing out of some object, you have a bunch of stuff leaving, but then you're replacing it with essentially the same size arrows from the sides. Does that make sense? And so that's why you should have a divergence of 0. You got the same amount of stuff coming in as you have going out. Our next one, right, we had a divergence of 2. Again, don't worry about the exact value. But here you can see, right, again, with this box, everything's just leaving, right? It's getting pushed out. And so the positive divergence means you're sort of becoming less dense. Your stuff is flowing away from your source. Okay? And then here, let's see, what was this one? 0 as well, right? And again, you get some flow in, some flow out, essentially the same thing as that first one, right? Here you can see everything's now flowing in with this example, right? And we had a negative divergence, so that negative divergence means you're accumulating sort of density of fluid there. This one also was what, 0? Oh no, this one was that mess there, right? Oh no, this is the bottom one. Okay. So y squared minus 4. This one's a little less obvious. You'd want to sort of narrow your y's down a little bit, but you could. You can see, like, if we're here, if you took a box down here, right, you have the same amount of stuff coming in as you have going out. So this one would be more. You'd really have to think about a smaller region than we were on the other ones, because it's hard to see, but like on this this area right here, you have arrows coming up here and then arrows coming down, right? And so you should expect you have stuff flowing in there, right? So you're flowing in some places, and then you're getting 0 here where you should have, well, I don't know. You're still kind of flowing in, I guess. Maybe I should broaden my window here. I'm only at -1 to 1. Let's see. So this one will be what? Positive if y is greater than 2 or less than -2, right? And then it'll be negative in between the two. So let's maybe open up our window a bit and see if that gives us a better idea. This might be too much. Again, they don't really talk about this in this section, but I figured it's in. Whoa, I did not like that. Oh, that's because I'm not. Oh, 2 negatives. Yeah, that's not any more helpful. Problem is that those middle arrows are so tiny that when it makes the right comparison, what if we just go to 5? Maybe that'll be better. And that's no better. That's exactly the same. What if my axis just... I don't know that that's that much more helpful. Yeah, I think I'll leave it at that. I just wanted that brief idea of what was going on with divergence. So we'll come back, we'll talk about that more as we move on a little bit further. But let's introduce curl as well. So this is another sort of operator on a vector field. And so the curl will be important as well. In this section, as you go through the homework, you'll see it's really just a matter of practicing some computation. And so curl, as we'll see later on, gives you a vector. And so the idea of curl is if you have a rotation in a fluid, think of it in 3 dimensions. Suppose you have, some fluid flowing through here and there's some little swirl of fluid right here. Well, that fluid is swirling around this way. And if you do your right-hand rule that you're used to from before, your thumb is going to point in the direction of the curl. So if your thumb's pointing like this, if your curl vector is pointing like that, you know your solution is sort of swirling around here. And then the size of the curl is sort of the speed that that stuff's spinning around. Okay. So again, all of that will come up later on. For right now, we're just practicing doing some computation. And for the most part, it's just a tool that tests whether a vector field is conservative or not. We'll see where all of this comes into play there. So when we define curl, we need a 3-dimensional vector. We might ask about the curl of a 2-dimensional one. Just throw 0 on the end, because you're always, right, you can't do your right-hand rule unless you're in 3 dimensions. Okay? And so the curl of f I'm going to write it like this, curl of f. And so I'm just going to basically use this as the definition. Okay, so rather than doing the dot product of that del operator with f, I'm going to do a cross product. And so a cross product looks like what? The determinant of this 3 by 3 vector, but now that del is are these operators, right? I think I'll just take my time and write this whole thing out in all of its detail. Okay. And so what you should get is what? I times what determinant? Right, you cross out that top row, right, in the left column. And so it should be partial with respect to y, partial with respect to z, q, r, and then minus, right, partial x, partial z, e, r, j, right, and then plus partial with respect to x, respect to y, p, q, k. And so you could memorize this, I suppose, but you really shouldn't. You should just think of it as being this. So that first term will be the derivative of r with respect to y minus q with respect to z. Does that make sense? So it's r sub y minus q sub z. What's the middle term then? Let's leave it negative, and then r sub x minus p sub z. Is that okay? And then finally qx minus py. Make sense? So again, for this section, it's really just a matter of practicing computing curls rather than doing anything else with them. So let's look at examples. Okay, you have, let's just do a few of these. So there's your first one. I'll just keep them pretty easy here like we did before. I'm going to just squeeze them all together. No, I'll write these in here. I'm going to do two-dimensional ones as well. All right. So take a few minutes, try to compute these, focused on these three-dimensional ones first, and then we'll come back to the two-dimensional ones. And as I said before, with the two-dimensional, just add a 0 into your third column when you compute your determinant. Alright, so let's just go through these again. Practice this yourselves, however you want. I'm just gonna do this. So that, okay. So the curl of f, right, you're just gonna follow that determinant. You can do it however you want. I'm just gonna go like this and put this up here. Right, take your time and write them out, do them however you need to, but your first one will be, right, partial of y with respect to this, so it's 1 minus this with respect to z, which is 0, is that okay? And then minus, it'll be this with respect to that, which will be 0, and then minus 0, is that okay? And then finally, the last one will be this with respect to x, 1 minus that with respect to y, so plus 1, right? You should get 1, 0, 2, is that what you got? Okay, and again, take as much time as you need to. I think we've done enough determinants that hopefully...
Am I able to just memorize
this
the
here?
formula and plug in?
Memorize this formula? Yeah, I mean, you can. I would just say it's really easy to forget it, right, in the middle of something and forget which one's where. And so it's much easier to remember this, right, determinant that you're doing this guy, cross this, especially since we're already doing the del operator dotted with f. If you just remember both of them, it's by far the better way to do it. But I'm not gonna hold you to it. Just think about, a year from now, if you tried to memorize this formula, it's very unlikely that will stick, whereas this, just a quick, oh yeah, the curl's the cross product, it'll jump back to you. So, I would learn it as a cross product for sure. Okay, next one here, same thing, partial x, partial y, partial z, and so the curl is what? So we cross this, so 0 minus y, comma, so it's negative z minus 0, right? It's negative z, and then finally 0 minus x. Is that okay? Okay. All right. And so let's do these 2D ones. So again, the first one is just x comma y, and like I said, if you want to do a gradient, a curl, you always throw in a third dimension, so you toss in 0. Okay, and then let's look at what that is. So I'm just going to do it this time, x, y, z, well, that'll be confusing. Partial x, partial y, partial z, right? So what do we get? 0 minus 0, 0. Remember, there's no x and y, or there's no z in this at all if you're doing a two-dimensional one. So these are always both going to be 0. Right, because you have no z's in here, so those partials will always be 0, and then this is 0. So it's really just that last term you're going to get. And what will this one be? 0 as well. And then d, so here's our f negative y, x, 0, and again I'll throw in these operators. So this time, right, 0, 0, and then 1 minus negative 1, so 2. Okay? So you do get a curl on that. And so let's look at the graphs or the vector fields of these guys. All right, there's too much going on. There's to erase this. let's look at these two we just did. And so here you got, well, it was just x, y, right? First one. And so there you have that. There's no sort of curling going on anywhere, right? So you should expect this 0 as, you know, as your vector. There's no curl anywhere. The other one, we came up with a curl, what was it? Negative y, comma x. And so you can see there is this swirling action of this, right? And so everything is rotating around. And so if you think of, right, if this is your x axis, here's your y axis, right? And so you curl around this way so your thumb is sticking straight out in the z direction, right? X, y, and then the z would be coming out at us, and so your curl's pointing in the positive z direction, and that's what we came up with here. Okay? So again, in this section, we really aren't worried about any of those, you know, details about where things are pointing. It's just practicing with some partial derivatives and getting used to these ideas, and then we'll see why the curl and the divergence are so important as we continue on in this chapter. Any questions on any of this? Okay. So.